So that then brings us to the final topic of this lecture, which is what is science and what does this involve? Science is a process, and it's a process by which we collect knowledge about a specific topic. That process is usually called research. So we've already gone through what the scientific method involves, and you should already know by now that it is definitely not a simplified linear type of process. So the nature of science is very complex. Like I said, it usually you go back and forth between different aspects of that process. So there's a lot of time spent in exploration and discovery that will help you formulate your hypotheses, and a very important part of that is being able to test that hypotheses, coming up with some conclusions. Another important part of science is being able to communicate that to the community and getting feedback from the community that will then help you revise, formulate other hypotheses, and adjust your testing. And another important part of science is to have some sort of societal benefit where your work is benefiting the community as a whole. And there's many different areas where these interconnect and build off of each other. So there's two different types of main reasoning in science. We call them inductive and deductive reasoning. So inductive reasoning uses specific examples to validate a very broad conclusion. Deductive reasoning, on the other hand, will take that broader theory and use that theory to develop a hypothesis and then make predictions. We usually call those predictions the hypotheses, null hypotheses being H naught, and alternative hypotheses being HA. Null hypotheses usually refers to there being no effect of whatever you're testing, while the alternative is what is that effect and what would that cause in your system. So an example of inductive reasoning would be, say I picked 2 nickels from a bag, so because I picked 2 nickels from the bag, I inductively reason that the bag must be full of nickels. But deductive reasoning, on the other hand, would state that, well, if this bag is full of nickels, then every coin I pull out will be a nickel. So inductive reasoning seeks to prove a conclusion, while deductive reasoning does the exact opposite. You go out to seek to disprove that conclusion. The only way you accept that conclusion is if you cannot prove it to be false. So we call inductive reasoning bottom-up reasoning. This is mainly used to develop hypotheses and theories, while deductive reasoning is called top-down reasoning, and it's mainly used to test hypotheses and theories. So some key terms that you should know. What is a hypothesis? What is a theory? And what is a law or principle? It's important to be able to compare and contrast these, specifically meaning what is similar and what is different between these terms. So a hypothesis is a tentative and a specific explanation for some sort of observed phenomenon, whereas a theory is very broad, and it's a broad explanation for the observed phenomenon, but it includes many different lines of evidence and many different hypotheses. A law or a principle, mind you, is the expression of some sort of mathematical or physical relationship. So this can also be pretty specific, but it can also involve many different equations, many different variables from other lines and other experiments. So it can be very specific, but it can also be a little bit broad. It kind of lays in between a hypothesis and theory. What is common with all of these is that in order to be science and scientific, all of these need to be based on observations, all of these are testable, and all of these can be used to make further predictions. So some other key terms that you should know is what is qualitative versus quantitative. So a qualitative type of variable is anything that can be observed, but you can't actually measure it. Something like your opinion, a behavioral response, a color. A quantitative variable, on the other hand, is anything that can be measured in numbers. So you can actually quantify something. So the length of a wing, the pH of a solution, the height and weight of an individual, all of these are quantitative type variables. Qualitative variables can be subjective. If somebody comes in and sees this as a bright blue, whereas somebody can come in and see it as a paler blue. So your color can be subject to the observer. So that would be something qualitative. Whereas a quantitative variable is more objective. There can be a little bit of subjectivity in how, say, a ruler is read between individuals, but in the end, you have a physical measurement that you can take, and the measurements that result from it are going to, they might vary a bit, but they're going to centralize around a common measurement. Qualitative variables can be very helpful in the beginning and also at the end of research. So it's not as if qualitative variables have no context or have no value in science. They definitely do, but they're going to be helpful in different ways. So qualitative variables can be very helpful in formulating a hypothesis. Then you can develop quantitative variables to measure. They can also allow for a broader interpretation of your study. So what is the bigger picture? How is this going to affect things on a community type level? That might involve your qualitative variables. Quantitative variables you can actually analyze with statistics because you have specific values, and they can be very helpful to validate your hypotheses, validate or falsify your theories, and also to form conclusions. So what is important in designing a valid experiment? And this will pertain specifically to your labs. So when you are carrying out experiments, you usually have one or more variables that you can manipulate. And when you're conducting an experiment, you want to manipulate these variables and you want to see what that manipulation causes. So you want to measure the effect from that manipulation. So these are going to be carried out to determine if there is a causal relationship or if you can quantify the magnitude of response for a variable. You're going to have two different variables. You can usually classify your variables as being independent or dependent. An independent variable is what you are changing or what you're controlling, whereas a dependent variable is what you're actually measuring, so what you're quantifying. A good experimental design, it's really important that you involve controls in an experimental design. So controls are important because they provide a measure of variability that's naturally in your system. They're also going to be important for checking for sources of error. So you can have both positive and negative controls. A positive control is something that you do that you already know is going to give a result. You already know it's going to show an effect. Where a negative control is something that you know to not give any result or effect. So a good experiment should also be replicated, and a good experiment should also be verified. So you should be able to carry out an experiment many, many times, and you should be able to get consistent results. Here we have an example of an experiment, and I want you to pay attention to what the dependent versus independent variable is and also what the controls are. So this is an experiment that investigated the effect of coat color in mice and how that relates to habitat performance and survivability. Here we have the beach habitat. And in this experiment, we have two different model mice. We have a light model mice, which has white coat color, and a dark model that has brownish color. In this type of environment, the beach habitat, the camouflaged mouse, or the light model, was considered to be the control because it is well camouflaged to the environment, and that would be considered the control in this type of experiment. Whereas the treatment effects, if we're looking at the effect of coat color, the treatment effect here would be the dark model mouse. And if you take a look at their performance, so the percentage of attacked models, you can see that there was a much higher attack rate in the dark colored mice. So in this experiment, coat color would be considered the independent variable, whereas the attack rate would be considered the dependent variable. The control here would be the white mouse, and the treatment would be the dark mouse. However, in the inland habitat, we have the opposite. So in this habitat, it's considered to be there's more vegetation. And so in this instance, the camouflage mouse or control mouse would actually be the dark model, whereas the treatment mouse would now be the light model or the white mouse. So in the inland habitat, you can see that there is a much higher percentage of attack on the light-colored mouse. So we would be able to conclude from this experiment, after you did the statistics of course, that coat color does affect the mouse and does affect their survival rate. So in conclusion, I would just like you to think about the ethics that can be involved in research. So you're going to be conducting experiments, you're going to be going on in your education, you're going to be reading more scientific studies and interpreting them and critiquing them. So it's always healthy to have a healthy level of scientific skepticism. It's important to note that just being a skeptic does not mean that you doubt or you don't believe something. It just means that you want to see the data. You're not going to make a conclusion until you see the data and how that falls. And you should be able to investigate how that data was collected in order to see how confident you can be in those results. So any claim that can't be tested using this scientific method, by definition, is not considered to be science. So here we've got Dr. Wakefield. So to give you an example of how important skepticism should be, Dr. Wakefield is the person who first published the study linking vaccines to high levels of autism in children. Since then, there have been many people, celebrities included, Jenny McCarthy for one, that have grabbed onto this study, presented this study, believed it to be true, and used it as evidence to support their conclusion that they should not get their children vaccinated, because if they get their children vaccinated, they would be subjecting their children to a high risk for developing autism. Now, since then, there's a lot of things that have happened in the scientific community. So that study was out for many, many years, and many scientists tried to validate it, and they were not able to validate these results. Over time, there's more scientific research was being devoted to this, more people were studying this, more people were talking amongst each other, and eventually it came out that he actually fudged his results. So because nobody could ever replicate his results, they asked for the data. When you publish anything, the data is open access. So anybody can write to you and ask for your data. So after many people started communicating with each other and communicating the fact that nobody could replicate these results, there was a careful evaluation of his data collection methods, of his data sets, and it turns out that most of his data was falsified, it was obtained in unethical ways, and the numbers just simply didn't add up. And so he has been completely discredited as a doctor, he's been completely discredited as a scientist, he's lost his job, but unfortunately, that hasn't been communicated widely to the public community. And so there's people that still rely on this study and his findings as justification for not getting children vaccinated, and it's simply not true. And so as a result, what we're seeing now is a return of many of the viruses and diseases that were eradicated due to vaccination. So once again, it is always healthy to be a little bit skeptical of what is presented in front of you, and you should be educated enough to be evaluating things properly to make your own decisions.